Hi there! In this video, we are going to be talking about a medical device. Now, I am not a healthcare professional of any sort and have absolutely no qualifications to be giving medical advice whatsoever. And so, I won't. This video, like nearly all of mine, is born from simple curiosity about how something works. My goal is to show you an example of how everyday technologies can be used in clever ways which improve our lives, not to make suggestions on how to do so. To that end, I'll be explaining what the device does and how it works, but not how, or even whether, it should be used in any given situation. And with that, let's continue. If you've ever made an unplanned visit to a hospital, you might have had this happen to you. Someone appears with a clip-like device, puts it around your finger, and it lights up with a couple of numbers. That device was a pulse oximeter, or oximeter if you want to say it that way, and it measures your blood's oxygen saturation as a percentage. This serves as a quick but limited snapshot of how well your respiratory system is functioning. I've got one right here, and simply by pressing this button and then sticking my finger into it, it tells me my heart rate and my oxygen saturation in moments, and completely non-invasively. Now, if you know a thing or two about blood, you'll probably know that in general, it should be inside your body and not outside of it. Usually, to analyze something about your blood, you'll need to get a sample of it through means of various unpleasantness. But this device manages to do without that. How? Well, with a sensor, and a very, very ordinary one at that. So first, what is a sensor? Or as they say in Star Trek the Motion Picture, a sensor. That's a surprisingly complicated question. Our bodies are filled with sensors, like the light sensors in our eyes, the temperature and pressure sensors in our skin, or the pressure sensors in our ears. Wait, you ask, pressure sensors? Don't you mean sound sensors? No, and that's precisely the point. A sensor is, on a very low level, something that reacts to a change in its environment or stimulation. But it's how we interpret that change that makes a useful sensor. For example, our ears detect rapid changes in air pressure, but that alone isn't sound. It's the way that our brains interpret that change that produces the sensation we call sound. Similarly, the photodetectors in our eyes simply send stimulation to the brain. It's up to our visual cortex to synthesize that stimulation into a useful image. Moving into the artificial realm, our human-made sensors work in essentially the same fashion. For example, take a thermistor. Its electrical resistance changes depending on its temperature. That by itself isn't useful to us, but if we study how that change occurs and learn the correlation between a given resistance and a given temperature, we can measure its resistance in order to determine its temperature. In that way, we can design a temperature sensor using a thermistor. A pulse oximeter is one of countless examples where we use a simple electrical device as a means to determine something. In this case, we use light. If you take a look inside where you put your finger, you'll find a little blinking LED. As your finger approaches it, it lights up solid. Now look on the other side and you'll see a photodiode opposite the LED. Your finger goes between the LED and that photodiode, and the oximeter shines light through your finger. If you were ever a child, which you were, you'll have discovered that your skin is actually quite translucent, and you can shine light through your thinner parts like fingers or earlobes. It comes out red on the other side because blood! And that of course means you're shining light through your blood and it's absorbing some of that light. And because scientists can't help themselves from asking questions and performing experiments, to which we owe them our thanks, we learned that the absorption spectrum of hemoglobin, that's the protein in our blood that carries oxygen around the place, is quite different between its oxygenated and non-oxygenated states. In layman's terms, this means it changes colors, but it's not nearly as drastic as the pop culture myth that deoxygenated blood is blue, because it's not. But it is enough of a difference to be measurable. And you can make the difference quite obvious if you measure it with two different wavelengths of light. Here comes a twist. There are actually two LEDs down there. There's a red one and an infrared one, and they're actually pulsing, not steady. The light flashes red, then infrared, and then off, over and over again. And by analyzing what the photodiode on the other side sees after the light passes through your finger, we can actually determine how oxygenated your blood is with fairly good accuracy. Look at this graph. This is the absorption spectra for oxygenated and deoxygenated hemoglobin. The red LED's output is right about here. Oxygenated hemoglobin absorbs hardly any of this wavelength, but deoxygenated hemoglobin absorbs a fair bit. As we move into the infrared range, this actually flips. The infrared LED's output is right about here, where oxygenated hemoglobin actually absorbs a little more light than deoxygenated hemoglobin. But there's more in your fingers than just blood. There's skin, there's bone, there's a fingernail, and other goodies. So how can light alone tell us anything? Well, because your blood isn't just sitting there in your finger. It's pulsing thanks to that heart thing in your chest cavity. With a little signal analysis, the microprocessor inside the pulse oximeter can isolate that pulsing component of the signals it's receiving and ignore all the not blood. That allows it to tell you your heart rate, but more importantly, it allows for the next most important bit, determining what percentage of the hemoglobin is oxygenated. Once the microprocessor isolates the pulsing of your blood, it simply has to make a comparison between how much infrared light passes through and how much red light passes through your blood during that pulse. That ratio itself will change over time as your cells absorb the oxygen and each new pulse refreshes the blood. A simple lookup table can then convert the peak ratio observed to the percentage of hemoglobin which is oxygenated, and then that value is displayed as SpO2, or peripheral oxygen saturation. This method has good enough accuracy to make this an acceptable tool for a quick snapshot of someone's respiratory function. There are many applications for this technology. A device like this is a simple indicator meant to give a one-time reading. This would be useful in an application like patient triage or a simple health checkup. In fact, the display is oriented for it to be read more easily by someone other than you. But there are also styles where the sensor is placed separately from the microprocessing unit to allow for things like logging of oxygenation data over time, which can help with diagnosing things like sleep disorders. Pilots who fly unpressurized aircraft may use these as a sort of early warning device. If your blood oxygenation falls too much, you may be near hypoxia, and when flying a plane, that's not good. I mean, it's never good, but it's especially not good when you're piloting something that can fall from the sky. So wearing a monitor like this one, or otherwise checking your pulse ox every once in a while, can help you to not get in that situation by alerting you that you need supplemental oxygen or otherwise need to descend. But you should know that these are not perfect devices. There are situations where they can give false readings. One such situation is with carbon monoxide poisoning. To the pulse oximeter, hemoglobin carrying carbon monoxide looks the same as hemoglobin carrying oxygen, so it may tell you your SpO2 is fine when in fact it's very not. There are specialized versions of these devices which use additional wavelengths of light to look for carbon monoxide poisoning, but the common pulse oximeter cannot do this. Some fingernail polishes purportedly interfere with the device's ability to function. In theory, it should be able to filter out the influence of such a polish like it can your skin and bones, but depending on what the polish might absorb, that may be impossible. Of course, there are other places where a device like this could work, like your earlobes, but the fingertip is the most common. And there are other situations where it might not be able to get a good reading. To help with this, many oximeters like this one will have some sort of pulsing indicator like this or other means to show you roughly how good of a reading it's getting. But the most important thing these devices can't do is tell you anything else about your blood. Arterial blood gas sampling, where you actually get some of your arterial blood out of you and analyze it in a lab, is the only way to know oxygen saturation precisely, as well as learn other things like carbon dioxide concentration, blood pH, or even how much hemoglobin is in your blood. However, the process of getting blood from your arteries is unpleasant. You can't just draw it from your veins because then that's not oxygenated blood, so, well, you get the picture. However, as a first check, these are quite useful. And since they're really just two LEDs, a light sensor, some sort of display, and a basic microprocessor, they're essentially commodities at this point and are accordingly pretty cheap. When demand hasn't peaked anyway. All it took to create this device was someone studying hemoglobin, discovering that its absorption spectrum is very different between its oxygenated and deoxygenated states, and then applying that knowledge. Knowing that red and infrared wavelengths would be affected differently between the two states, and making the connection with available light-emitting diodes allowed Takeo Aoyagi and Michio Kishi to develop the modern pulse oximeter in 1972. I say all it took like it was easy, but it goes to show that our world is made of discoveries built on top of one another. When we learn things about ourselves, we often find ways to apply that knowledge. Sometimes it happens long after we've made the first discovery, or perhaps, as was the case with pulse oximetry, we knew the basics of it since the 1930s, but it took until the modern technological age for it to become truly practical. But learning new things and applying that knowledge is what makes us human. When we do it, it can not only blow your mind, but can save your life. I'd like to end by saying that these are obviously an invaluable tool. They provide quick access to vital information about our bodies, and because they've been refined through the decades and the technology that's inside them is very cheap at this point, they're easy to purchase. But I'm not about to say that you should run out and buy one. If it interests you, I would encourage you to do your own research on what to look for, both in terms of the devices themselves and how to interpret the data they provide. Because again, I am not a healthcare professional, I'm not an authority, and I don't want to be perceived as one. The only conclusion I want to lead you to today is that these are pretty neat, and human ingenuity is awesome. Thanks for watching. Okay, this video is something like 11-12 minutes long. If I cannot record this in less than a half hour, I'm going to be very upset at myself. Hi there, 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 hi there. Discovering that its absorption spectrum is very different between its oxygenated and deoxygenated globin. Discovering that its absorption spectrum is very different between its oxygenated and deoxygenated. This video, like nearly all of mine, is born from some, nope, don't like that. As your finger approaches it, it lights up solid. And it stopped. To percentage of hemoglobin which is oxygenated. There are a lot of big words. No. So wearing a monitor like this, or otherwise checking your finger in it, it tells me my heart rate and my oxygen set up, but this device manages to do that without, nope, for that change that produces the sensation we call sound. Similarly, don't write that word.